No, I've never seen it using this really ultra fast camera, and it reveals quite a lot of stuff about the chemistry, you know, so it's an interesting video that you're putting together. Now if we just talk about the chemistry for a moment, yeah, we take an oxidant, so something which delivers oxygen, and in this case we use a molecule called N2O. Okay, this is laughing gas. Classically the experiment used NO, and NO has some issues over perhaps uncontrollable side reactions, particularly with oxygen, that we try to avoid when we do this reaction. So we use N2O. It's also much easier for us to use because we get it out of a cylinder and we don't have to generate it and then collect it over water. So I fill up a large test tube with N2O, and the test tubes can be small, you know, about 3 feet long, or they can be 5 feet long, so some really quite significant tubes. And then you put a small amount of carbon disulfide into the tube itself, and that's the fuel, that's the source of carbon, okay? And the reason why we use this is because the boiling point of carbon disulfide is very close to room temperature. So just by shaking it with water, we can make all of the fuel go into the oxygen-rich N2O and form a really quite spectacular combustion mixture. Now to initiate the reaction, you add a match to the top, and then you see this fantastic bluey green hue of a flame, okay? And the flame races to the bottom of the tube. And there are a couple of things that we often talk about. We talk about the heat of the chemical reaction getting hotter and hotter, and I suppose accelerating the rate of chemical reaction as the tube sort of is combusted. But there's a second point which is often missed by people, and that's the fact that as the flame front gets hot, it pushes down on the combustion mixture underneath it. So it increases the pressure of the unburnt gas mixture underneath. So again, the chemistry goes a lot faster. It's accelerated because of temperature and also of pressure. And I thought that this flame front used to go very smoothly from the top to the bottom, and hence the whoop. But actually what this video footage has shown us is that it actually goes in stages. It sort of goes it sort of chugs its way to the bottom of the tube. And I think this is because the reaction is so fast that it consumes all of the gas fuel molecules that are in front of the flame front too quickly. So it pulls all of the molecules in, reacts them, and generates a lot of heat. But eventually diffusion is not fast enough to bring more, I suppose, fuel molecules to the flame front to continue with that rapidly accelerating flame front. So it has to stop and pause for a moment, perhaps gather some breath, as diffusion brings more fuel molecules back. Now as it gathers its breath, the intensity of the flame goes down, so it gets a bit cooler, and that leads to a contraction in all of the hot gases that you're generating above, and the flame front seems to like pull in and go back up the tube. And if you look at the top of the tube, you actually see these puffs of smoke coming out periodically, which correspond to the relaxation or the time out moments that this flame is actually going through.